taking a look at vectors. Okay, so from our understanding, previous understanding, we know that the difference between scalar and vector is the scalar has magnitude, while vector has magnitude and direction. Okay, so we can say scalar quantities, the difference, scalar and we have vector quantities. So this has just magnitude, but no direction, and the vector quantities have magnitude and direction. Now, examples of scalar, we have length, and we have area, we have volume. Okay, and we also have mass. And examples of vectors, okay, which have both magnitude and direction. We have force, we have velocity, we have acceleration, okay, we have weight. Okay, so the question is, how do we represent vectors? Okay, we are in mathematics and not in physics. Okay, so let's say a vector line ranging from A to B. Okay, so the vector is moving this scalar in the direction of A going to B. Okay, so vectors generally can be represented by a line. Okay, like we have just done, and we can also represent it with bold values, bold letters. Okay, such that it will be very bold. But most of the time, we represent it with something with an arrowhead for the ease of identification. Now, when we come down to components of vectors, vectors have three components in general. We have the I component, we have the J component, and we have the K component. Okay, the I component is similar to the X direction. The J component is representing the Y direction. The K component is representing the Z direction. Okay, so now if we can draw a Cartesian plane for this, we'll have the X direction and as usual the Y direction. Now the Z direction can come in this manner. Okay, so this is our Z direction. Okay, so we can have vectors, okay, ranging in any format with different values of I, different values of J, and different values of K. Okay, so let's say we are given question 1. Let's say we are given Z1 to be equals to, as a vector, to be equals to 2I plus 4J. Okay, and we are given another vector, this is Z2, to be 5I plus 2J, and we are requested to draw it on the as vector components, okay, on the component diagram. So as usual, we would have our Cartesian plane in response to it, and we will label them accordingly. Let's go to 1, 2, 3, 4, 5. This is in the I direction, or what we call X. Okay, so the X is similar to the Y, and this is the X is similar to the I. Okay, and this is the minus X. For this minus 1, minus 2, minus 3, minus 4. Now going further to the Y, we can also have 1, 2, 3, 4, 5, and minus 1, minus 2, minus 4, minus 5. This is minus Y. Now the Z1 would have 2I. You can see that this is 2I here, and we have 4J here. Okay, that's 4 in the y direction and 2 in the x direction. So just like we have with plot graphs, we want to know A to B, so then we can now further draw a line. Okay, so we will call this line on the direction moving from the origin to Z1. Now we can also draw for Z2, and it is as 5, that's 5I, and also 2G. So we'll join the locations together and join. Okay, so the arrow there shows that this represents Z2. Alright, so we can now draw the component diagram. Okay, then let's take a look at addition and subtraction of vectors. It is very easy. Let's take at addition and subtraction of vectors. Okay, now given we have 2I, Z1I equals to 2I plus 4G, like we had before, and Z2 equals to 5I plus 2G. And now we are required to find A, Z1 minus Z2, and B. Okay, we can start with plus Z1 minus Z2. Okay, so how do we go about this? Okay, so as usual, let's just substitute our values of Z1 and Z2, put them in brackets. That's 2I plus 4G plus 5I plus 2G. Okay, so let's open the bracket, it's positive. That's 2I plus 4G plus 5I plus 2G. And we can collect like terms together. That's 2I plus 5I plus 4G plus 2G. And 2I plus 5I will give us 7I. And 4G plus 2G will give us 6G. And moving forward, now let's evaluate Zi minus 2I. So the first thing to do is to substitute our values. Okay, so that means we have Z1 to be 2I plus 4G, the subtraction sign, and 5I plus 2G. Now we can open up brackets with negative, so we have minus 5I plus, that would be minus 2G. Now let's bring the I together and bring the J together. Minus 5I plus 4J minus 2J. And this gives us minus 3 plus 2 minus 5 is minus 3, and plus 2J. Okay, so questions can come in various forms. Now imagine we introduce a new Z3 component. Okay, so let's say imagine we have a Z3 component, and let's call it I plus 2J, and it has 3 components. Let's say plus K. Okay, now we might be required to find let's call that C, Z, Z1 plus Z2 minus 2Z3. Okay, so As usual, the first thing we'll do is to substitute values of z1, z2, and z3. Let's also not forget our arrowhead. So z1 is 2i plus 4j. Okay, z1 is 2i plus 4j, and z2 is 5i plus 2j. That's 5i plus 2j, and z3 is I plus 2j. Okay, I plus 2j plus k is I plus 2j plus k. Now, this is multiplied by 2, and there is a minus sign there, there is a plus sign here, and we add our brackets. Okay, so now we just have to open up the brackets responsibly. So that's 2i plus 4j. We open up this bracket with plus 1. That will give us plus 5i plus 2j. And then we open up this bracket with minus 2. Okay, so minus 2 multiplied by I give us minus 2i. Minus 2 multiplied by 2j give us minus 4j. And minus 2 multiplied by k give us minus 2k. So with respect to that, we can bring the I together. So this will give me 2i. Okay, we have I, I. Okay, so this gives me 2i plus 5i minus 2i. Okay, and the j components, we have j, and j. So this gives us plus 4j plus 2j minus 4j, and we have just one k component. Okay, and that gives us minus 2k. So 2i plus 5i minus 2i will give us 5i. 4j plus 2j minus 4j plus 2j, and since we're left with just a king component, so that will give us minus 2k. Okay, so let's pick one more example. Okay, z1, z2, and z3. Now let's say we are required to find z1 minus 2z2. Okay, we can call this 4z1 minus 2z2 plus z3. Okay, so as before, we substitute our values for z1, z2, and z3. Now z1 is 2i plus 4j, z2 is 5i plus 2j, z3 is I plus 2j plus k. Okay, and we know there's a positive sign here, there's a minus 2 here, and there's a 4 here. So all we just have to do is open up the bracket. The 4 multiplied by 2i will give us 8i. 4 multiplied by 4j will give us 16j. Minus 2 multiplied by 5i will give us minus 10i. And 2 minus 2 multiplied by 2 will give us minus 4j. And if we open the bracket with 1 here, we have k. So we can bring the I together. I. That gives us 8i minus 10i plus I. Okay, and let's call this j, and j. So we have plus 16j minus 4j plus 2j. And here also we still have just a single k. Okay, plus k. So 8 minus 10i plus I. So this will give us 9 minus 10, which will have as minus I. And plus 16 minus 4j, 16j minus 4j plus j. So this will give us 18 minus 4j. And at the end we'll have it to be 14j. And then we'll have plus k. Okay, so literally that's how it is done. And what if we are asked to find the modulus or the magnitude of the vector? Okay, magnitude modulus of vector. So magnitude of modulus. Okay, modulus of the vector. So we will still go back and use these three vectors we are from scratch. Okay, and we use it to evaluate the magnitude of each vectors. Okay, so let's go back and say z1. As you know, is this is z1 here, this is z2 here, this is z3 here. So z1 is 2I plus 4j, and z2 is 5I plus 2j, and z3 is I plus 2j plus k. And we are required to find the magnitude of each vectors. Now the magnitude is written as z. Okay, written like this. Okay, with these two parallel lines at the center. Now here is the rule of evaluating magnitude of the vector. Now we have this thing. If R is equals to AI, okay, plus BJ plus CK, then the magnitude, okay, if R, then the magnitude of the vector, which most times we write as modulus of R, okay, right, as modulus of R will be equal to the square root of A squared plus B squared plus C squared. Okay, so if we apply this now to the, okay, for this A, for this B, and for this C. So these vectors, okay, now let's apply it to these vectors, and then we will realize that z1, okay, z1 doesn't have a k component, so we can rewrite z1 to be 2I plus 4j and plus 0k. Okay, so we know that this is our A, this is our B, in comparing to this format of vectors, and this is our C. Alright, so our modulus of vector z1 will be equals to the square root of A squared, and since A is equals to 2, that will give us 2 squared, following the formula here, plus B squared, and that will give us 4 squared, and plus C squared, that will give us 0 squared. Okay, so with respect to that, we will have it to be the square root of 4 plus 16, and we will have root 20. Alright, continuing further, let's evaluate the magnitude of z2. Now we have z2 to be written as 5I plus 2j. Now it doesn't have a k component, and you can just write it as 0k. Now we know that this is our A, this is our B, and this is our C. Now the modulus or the magnitude of z2 will henceforth be the square root of, following the same formula we have as 5 squared, okay, plus 2 squared plus 0 squared. Alright, so which will give us square root of 25 plus 4. Right, 5 squared is 25 and 2 squared is 4. And at the end of it all, we will have it to be 29. And finally, C, we want to evaluate the modulus or magnitude of Z3. It give us I plus 2j plus k. Now this I here means it is 1I, okay, and this k here means it is 1k. Okay, alright, so we have this to be A, we have this to be B, and also we have this to be C. Now our modulus of vector or magnitude of the vector will be the square root of A squared plus 1 squared, B squared plus 2 squared, and C squared plus 1 squared. Okay, and that will give us 1 plus 4 plus 1, and 1 plus 4 plus 1 is 6, and we have our answer to be with 6. Now, having been able to evaluate modulus of a vector, we want to quickly look at what we call directional cosine. Okay, directional cosine, or we can just simply call it direction cosine. Okay, now the direction of a vector in 3 dimensions is determined by the angles which the vector make with the 3 axes of reference. Okay, so here is the logic behind it. Now we're given that if we have vector r, which is equals to ai plus bj, okay, plus ck, right? Then we know that the modulus of the vector, which we write as modulus r, is equals to the square root of a squared plus b squared plus c squared. Okay, now we can now go back before we conclude on the magnitude of modulus. We can now say that the magnitude of modulus of a vector is the square root, okay, of the sum of the square root of the sum of individual squared. Okay, so keep this in mind. So yeah, and let's go back to our directional cosine. So we're given a modulus, a vector quantity of r in as ai plus bj plus ck, and we know that the modulus, okay, will be modulus r, which will be equals to square root of the individual squared, and that was a squared plus b squared plus c squared. Now then our directional cosine, which we mostly write as n, l, as l, as m, okay, and as n. Okay, so if we write it like this, okay, the l, okay, is usually written in square brackets. Okay, l is in regards, okay, so the x-axis, okay, that is I component, okay, and m is in regard, okay, so y-axis, okay, that is in regards to j, and n is in regards to z-axis, okay, that is z. Okay, so it's always written in terms of square brackets, so l, m, n. Okay, so how do we evaluate our l? What is our l? What is our m? And what is our n? Okay, so our l is equal to a divided by modulus of r. Our m is equals to b divided by modulus of r, and our n is equal to c divided by modulus of r. Okay, now still on these 3 questions, okay, now we will be required to evaluate the directional cosine for each of these. Okay, now let's have our 3 questions: a, b, and c. So z1 is equal to z2 is equal to z3 is equal to. Now, so z1 is equal to 2I plus 4j, z2 is equal to 5I plus j, and z3 is I plus 2j plus k. So z1 is equal to 2I plus 4j, z2. Okay, let's go back and check. Z2 is 5I plus 2j, 5I plus 2j, and z3 is I plus 2j plus k, I plus 2j plus k. Now we are required to find the directional cosine for this. Now let's spice things up by changing some things to negative signs. Okay, and let's change also this to negative sign. So with respect to that, we have already calculated the modulus of these vectors before. Okay, so for z1, we have that the modulus is given as z1. Okay, and we've calculated that before. Or let's just write it down here. Okay. Now, this is z1 is equals to 2I plus 4j. Okay, and obviously we know that this is 0k. Okay, and our modulus of vector, for z1 that we calculated is root 20. Okay, root 20. So let's write that root 20. It's 20. Okay, and we know that 2 is equal to a, 4 is equal to b, and 0 is equals to c. Now there's our formulas for L, M, okay, L, M, and N, which are the directional cosines which we'll be looking for. Okay, and L is equals to A over modulus of R of the vector, and M is B over modulus of the vector, and N is C divided by modulus of the vector. So write L to be A divided by modulus of Z1, and M to be B divided by modulus of Z1, and N to be C divided by modulus of Z1. Now with respect to that, we know that our A is 2 and our modulus of the vector is 20. We know that our M is B is 4 and our modulus of vector is 20. It's 20. Okay, and N is 0 and our modulus of vector is what? It's 20, and this will eventually give us 0. So it's just as easy as that. Okay, just as easy as that. So let's pick up for the next vector. So we have z2, which we have to be 5I plus j. Okay, 5I plus j, 5I plus 2j. Now we've changed it to minus. Okay, we wanted to spice things up, plus 0k. Now we know that's usual that this will be our A, and this is our B, and this will be our C. Now our modulus of vector z2, which we calculated previously, is root 29. Okay, it's root 29. Yeah, that might be coming to your mind that is it all modulus that will have square root? And no, not all modulus will have square root. Sometimes it might be a number straight up when we perform the square root, and we don't. Okay, so sometimes it can be square root, which we can change for that into some numbers, and it can just be a whole number. Okay, so our L is a divided by square root modulus of vector 2. Okay, and our M is equals to B divided by modulus of vector 2, and also our N is equals to C divided by subsector 2. Okay, now we know that our L will be equals to 5 divided by root 29, and our M will be equals to B is minus 2 divided by root 29, and our N is 0 divided by root 29, which is equal to 0. Okay, now let's finalize on our last question. C, we know that Z3 is equal to I, okay, I plus 2I plus 2J minus K, I plus 2J minus K. Now, how do we go about this? I plus 2J minus K. We know that modulus of Z3, okay, is equal to, like we've calculated before, root 6, okay, that's root 6, and modulus of Z3 and our L will be equal to A divided by modulus of Z3, and our BM will be equals to B divided by modulus of Z3, and our C or N, sorry, will be equals to C divided by modulus of Z3. Now means that A is 1, okay, 1 is A, 2 as B, and minus 1 as C. Okay, that's 1 divided by root 6, and M will be equals to B is 2 divided by root 6, and N is equals to minus 1 divided by root 6. Now let's take another question. So we want to evaluate we're given modulus of R. Let's call this D, and this will be our last question. And we're given 3I minus 2J plus 6K. Okay, now how do we evaluate the modulus of the vector? Here we know that our A is equals to 3, our B is equals to minus 2, and our C is equals to 6. Okay, and we know that if we are given that, let's just do a quick back. As we're given a modulus of vector of AI plus BJ plus CK, definitely our modulus of vector will be equals to the square root of A squared plus B squared plus C squared. Now, the modulus of vector R is square root of A, that's 3 squared, plus B, that's minus 2 squared, and plus C, that is 6 squared. Now, we have it to be 9 plus 4 plus 16 plus 36. Okay. So because 6 squared is 36, so this will give us root 49, and root 49 is 7. Okay. Now we are requested to find the directional cosine of the vector. So we know that our L is equals to A divided by modulus of R. Okay, and our N is B divided by modulus of R, and our C is our N, okay, is C divided by modulus of R. Now our A is 3, modulus of R is 7, our N is minus B, that's minus 2, and our R is 7, and our N is C is 6, and the modulus of R is 7. Okay, these are the values of A, B, and C here. So it's just as easy as that. And in our next videos, we'll be looking at what we call scalar vectors and the scalar product of two vectors, and also vector products of two vectors. And furthermore, we'll be looking into the angles between two vectors. Okay, and we can also look at scalar triple vectors. which will be very, very important. Very, very important. Or vector triple vector.